You can see me all right?
Yeah. If you want to just start your slideshow.
Sure. Go. I think that's popped up all right.
Yeah, your slides are there. You just need to start the show.
All right. Thanks, Chuck, and welcome everybody. Thanks for coming. I hope that you enjoy the talk and that there's a nice discussion time afterwards. I think I've only got about 25 slides, so we should have time for that. And again, yeah, thanks for the invitation. I just want to start by saying that I'm really just a representative of a large group of people that have been working on this project. You know, we come from the University of Saskatchewan, Environment Canada, University of Calgary, and a number of other places where sort of some of the people that have been working for us have kind of moved on. So people have gone to Regina, Oregon, Calgary, and Yukon, but they've played an important role for us in some of this work. So I think it's important to credit them. So we've, as Chuck mentioned, there's been some recent publications that have come out based on some of this work. First in the Canadian Water Resources Journal, and this last one in the second one in the Conversation, which is a first for me, and it was kind of interesting to see that picked up by a number of other news outlets like the Western Producer and Globe and Mail and such. You know what, as Chuck was saying, it was some of the take-home messages from some of these articles in which we've been summarizing some of our work is just how important wetlands are on the landscape, and that they do have a number of functions that provide services that people value. And so they do have a place on the landscape, and they do have a place in sort of the agri-environmental system. And what we just need to do is figure out that sort of optimal distribution where we can sort of maximize as much as we can. So I think what I'll do is I'll start with sort of one example of functions that wetlands play, and that's groundwater recharge. And this is a really good example for the kind of things that are going on. And I'll try to keep the lingo to a minimum. I'm not exactly sure who's on the call, but I apologize if I drift off into too much of that. But what happens? I'm not sure if people can see.
Sorry to interrupt, Chris. You just maximize your screen there. We can see your panel and everything. So yeah, just start your slideshow.
Sorry. It's showing up on my big screen as maybe. Shoot, technology issue. Zoom slideshow. What do you see? Do you see just the slides?
Yeah, we see the slide view.
Okay.
Yeah, rather than the slideshow.
Okay.
What if you just hit on the toolbar, the top toolbar there, slideshow, and start from beginning?
Yeah.
Try that.
No, I think what's happening is it's showing up on I've got two screens going.
Oh,
and,
okay.
It's showing up on my big screen as playing, but it won't on the laptop, and that's what you folks are seeing. So
can you select that when you choose which screen which thing you're displaying? Your screen you're sharing, is that an option to choose the one that's in slideshow?
Let's try this. Oh, here we go. Is that better?
No.
And then
no. Oh, no, there we are. Now, yeah, now we have the slide.
Okay, you don't see it.
It is showing sort of what's next.
It does do that though.
Yeah, but that's better.
Is that better?
Yeah, it is larger.
Yeah, You're on a groundwater recharge slide now?
Yes.
Okay, I'm gonna back up. There, title slide, recent publications. Yeah, this is when I was talking about the Canadian Water Resources Journal and the conversation article. And then groundwater recharge. This is where I was. So sorry about that. I think 18 months in, we would have figured all these bugs out, but I guess not. Sorry. Anyway, so for groundwater recharge, this is quite an important function on the Canadian prairies. We've known for decades that most of the groundwater recharge that occurs in this sort of hummocky landscape occurs underneath depressions, and this depression-focused recharge happens in these wetlands. And however, not every wetland is created equal in this regard. Those in lower topographic positions tend to be discharge ponds where groundwater emerges to the surface. And so the groundwater recharge function occurs in those that are sort of higher topographic locations. So again, I'm not sure if you can see my mouse moving around, but this one here would be a groundwater discharge pond, but something like this one here would be a recharge pond up at a higher location. And but what Edward Bam learned over the last few years is that even recharge ponds don't always recharge the same over time. And some of that has to do with sort of the hydro period, or how long the water has been in that depression. So if you have, say, a permanent recharge pond that has water in it for a much longer period, the water table is actually sloped towards the pond like this, rather than away from the pond. So those types of recharge ponds actually don't recharge as much as those ephemeral ponds, the ones that last on the landscape for just like weeks, maybe months on the landscape, because of the way the water table is sloped away from those ponds. And that, so you get more movement downwards from those types of wetlands than you do from sort of the recharge wetlands that have water in them for more time. So what's complicating about that is that could be over time the exact same location. This is an example of Pond 109, and in academic circles, this is a really famous pond. This is where Masaki Hayashi got his PhD. It's in the St. Denis National Wildlife Area, just east of Saskatoon. And people have been measuring pond depths in this depression since the 60s. And it's super interesting to kind of see this pattern of these cycles kind of move through. And there was a period of time since, I know this sounds really strange for me to say, so since the turn of the century, that we went through quite a wet period. And Nicholas Kennard took a picture of Pond 109, I think in 2015. And at that time, water had been in that pond for 6 years or so without going away. So that would be considered a permanent recharge pond at that time. However, with this recent dry period, Andrew Ryerson took a picture of this same pond and it had dried up. So then it kind of begs the question, is this a permanent or is it an ephemeral recharge pond? And many of you may be familiar with the Stewart and Cantrin wetland classification system. And it basically classifies wetland depressions by how long the water stays in the depression. But there really isn't a classification for a pond that lasts for years but can go away for months or more years, right? As you can sort of see from the Pond 109 record. So it's kind of like a 4A or a 5 something kind of a pond. And for a long time, you know, somebody, if they were looking at this and trying to classify this pond, and this classification system is a foundational piece in, say, Alberta's wetland policy. If somebody comes along and looks at the pond like 109, in 2015, they would probably classify it maybe as a 5. But if they went to there today, it might be considered a 2. And so what's important to consider is that these wetlands are dynamic and diverse, and the same location can provide very different functions over time. You know, in the wet period, it provided very good duck habitat, but these days, maybe it's a better sort of groundwater recharge pond than it was when it was really good duck habitat. And so this kind of just goes to the message that Colin and I were kind of trying to promote in that conversation article, is that we need a diversity of wetlands across the landscape, because even in one location, you can have a variety of functions. So if you only have one kind of wetland on the landscape, say large consolidated wetlands down at the bottom of a watershed, you're really minimizing the level of functions that these landscape features can provide us. So starting maybe 5 years ago or so, there was a group of us, and many of us were listed on that front slide. There was a group of us in a global water features funded program called Prairie Water, where we're trying to really disentangle this dynamism, this diversity, not just of wetlands, but especially of wetlands, to create information that we think would be helpful for people so that they can maybe improve understanding of water cycling in the prairie ecozone, and make more informed decisions, and in turn enhance their resilience. I don't want to say become resilient, because I think clearly many prairie communities already are, but just to enhance that resilience. Because I think the next 50 or 60 years are kind of going to be tough. But anyway, if you got questions or comments, you can reach us at these places. And through the rest of the talk, I'm really going to summarize a lot of work that this group has done over the last few years to sort of achieve, move closer to this goal. And so what we did at the beginning of the program is that we sat down with our partners and our stakeholders and said, okay, what are you really concerned about? What keeps you up at night? And what I'm showing here is that 2 things in particular were high priority and interesting to everybody. Everybody cared about these 2 things, and one was wetland drainage and one was multi-year drought. And so that's what we decided to focus on in much of the work that we were doing. And thanks to a guy named Graham Strickert, who's on the team. I think you can pick him out in that picture on the left. But anyway, he suggests we kind of look at this through this triple loop learning process, where you start at the beginning and say, are we doing all the right things? Are our land use practices and our choices and things like that, are they the right things to achieve the societal goals we want to, right? So we wanted to address that. And then I think we started to get at answering some of those questions, but what we were hoping to do by the end of the program, which ends in a couple of years, is see if we could get maybe not into the 3rd loop, but at least into the 2nd one. Is that, are we doing things right, in the sense that, okay, we have some policies in place, but will those policies actually achieve the goals that we thought they would do when we designed them in the first place, right? So if we say we have a water management strategy that's going to do certain things, is it actually going to achieve those things? And what we're hoping to do in Prairie Water is develop some tools that will help us also evaluate some of those things, in terms of, if we're hoping to build the toolbox through which we can sort of help to evaluate policies and practices, maybe even before we enact them, but and also to evaluate current ones in place if people care to do so. And so a foundational piece of this is a catchment classification that Jared Wolf led. And what we found was that all 4,000, roughly 100 square kilometer watersheds in the prairie ecozone could be classified into one of 7 types, and that's shown with this map. And this division can be it's based on soils, topography, climate, predominant tillage practices, wetland distribution, and from this, what we can find is that each one of these different basin classifications, be it sort of, I'll go back to this, sort of pothole till in blue, or southern Manitoba in purple, or the high elevation grasslands in Alberta, predominantly in Alberta, in red. Each has some characteristics that we can use, whether they be the number of wetlands, the tillage practice, the distribution of those wetlands, again, that slope. And we can use that to inform the construction of a model of a basin. And so what we're doing in this sense is that we're modeling the prototypical, pothole till catchment. We're not modeling any specific one. We're modeling, it's like we're modeling nowhere but everywhere, if that makes any sense at all. And part of the reason we chose this approach is because one of the criticisms of previous work, and there's been lots of work sort of trying to figure out how climate or land use may influence watershed response on the prairies, but it's that extrapolation elsewhere to across the region that people have always wondered about. Right? How representative are the research catchments like at St. Denis to other places? So we decided to do this sort of as a foundational piece from which to do this sort of extrapolating. So the results we get out of these virtual models aren't for any specific place, but they are representative of what we would expect to happen under some kind of stress, or under some kind of stress across a region in general. So then we took this virtual basin modeling approach, and it's incredibly flexible in the sense that if we take climate and the landscape and say, okay, we're going to build a model like this sort of image that Jared drew in the middle, and then we can simulate what we expect basin runoff to be, or snow water to be in those areas. And then if we change something, if you look in the left-hand side, we warm up Alberta, that's what it's expected to do. We can sort of see what might happen to basin runoff. And if I switch back and forth between the slides, you can sort of see the difference that might be expected with that kind of change. And so when we apply them across all the basin classes in Saskatchewan and try what we did was we manipulated the climate. And so what we did was we started with a baseline climate of 1965 to 2006 and incrementally warmed up the climate 1 degree each, and went to see in order to find out maybe what would happen to mean annual runoff. And what we found is kind of shown on this map, is that for every degree it warms up from that baseline period, the sensitivity of runoff to that warming is such that you would expect a 7 to 14% drop in mean annual runoff over a 30-year period, in that 30-year period, if it warmed up. And what's interesting about this map is you can sort of see that basin classification emerge. And so place matters in the sense in that some landscapes are perhaps more more sensitive to this kind of effect than others. In particular, you can sort of see that Missouri Coteau kind of pops out there a little bit in south central Saskatchewan. And so what we can also do is, if we start with that same model, with the same climate forcing a different landscape, we can also alter the landscape. And this is kind of how we get at things like wetland drainage. What happens if you start to remove wetlands from the landscape, or consolidate wetlands, take a bunch of small ones off and consolidate down at the beginning, at the bottom, which is, it's I wouldn't say widespread, but it's not uncommon practice in many places across the prairies to do this kind of thing. So what we did was, in order to find out what would happen with this, is that we took that virtual basin model, and over that pothole till landscape, which is more or less aligned with the prairie pothole region, and we forced that with 4 different climates, from Brandon, Estevan, West Battleford, Yorkton. And we really struggled with this one about how to deal with the sequence of sort of wetland removal and drainage, because it's so driven by local circumstances. And so we tried a number of different things. We drained from the top to the bottom to the top, large to the small, or the smallest to the biggest, and all to find out what would happen. And in general, what we found is it really doesn't matter so much. One really big take-home message is that there is no threshold below which wetland drainage doesn't increase stream flow volume. We see a response, immediately. And there's a lot of information in these box and whisker plots, and I think what's important to sort of interpret here is that this is for a 30-year run. So what you see in each box and whisker is sort of the range from the minimum runoff to the maximum runoff. You would see over that 30-year period, and that black bar in the middle is sort of your average condition. So there's still lots of variation within that 30-year period, but when you look at the whole regime, then you definitely see that removing these wetlands increases the discharge. What's interesting is that it's more or less a linear rate, but when you do remove sort of disproportionately large, what we call gatekeeper wetlands, you do see a bit of an uptick. And you can kind of see this in the top to bottom panel at about 30 or 40 sort of percent drainage by area, a bit of a tick up. And that's because in the wetland distribution we use, the largest wetland gets removed when we jump from that 30 to 40%. It sort of jumps up there, but those are sort of the big take-home messages here. And while this image kind of shows the whole regime, there are some nuances in this, because not every year is going to react the same, definitely, right? And I want to apologize right up front for showing this the information this way. I was practicing yesterday, and I thought about how the data are shown in this particular slide, and this is a classic sort of engineering slide where you've got runoff, annual runoff on the y-axis, and on the vertical axis, and return period, which is this terrible engineering term, which if you take the inverse of it, sort of 1 divided by 10 or something, you get sort of the chance that something will occur. So a 1 in 10 year flood would happen 10% of the time, a 1 in 20 year flood 5% of the time, that kind of thing. So as you move to the right hand side of the graph, those are sort of your lower frequency, higher runoff years. So they don't happen as often, but when they do, they're higher flows. And what you end up, one thing that's clear is that if you sort of move from that blue line, which is no wetland loss, to 100% wetland loss, which is pretty extreme. What was the 1 in 20 year flood is about 40 millimeters. Now actually occurs about once every 2 years. So that's the average condition. So those higher runoff conditions occur more frequently. But that on the other side of the coin is that what we find is that those average years, those median years around that 1 in 2 year return period, those increase disproportionately more than the extreme dry years. And why it is because in the dry years, there's not much rain coming out of the sky. And in wet years, everything's wet and everything's full. And so there's not a lot of storage capacity on the landscape, or the storage deficit is low on the landscape anyways. Whether somebody has removed it or through drainage, or it's just the ponds or the depressions are full. So you don't get as much of an increase in the wet years, though you do. And before I go any further, I want to apologize because they're renovating a bathroom in the house here, 3 floors down, and you can still maybe hear some of that noise. And I'm sorry about that. That was sort of bad luck that they decided to show up today. So, but such is the working from home. Anyway, the other thing that's really nice about this this approach, this foundation of virtual basin modeling, is that we can take this hydrological model and integrate it with other models, and we can sort of, for instance, take outputs from the hydrological model and use them as inputs into other models, or we can use some of the socioeconomic models that, say, something like Ken Belcher is using to inform how we set up the hydrological model and some of those sort of land use characteristics or wetland drainage characteristics. And so that's kind of the next step that we're moving to. And one thing that Crystal Antica was able to do, and Emily Cavalier, was to connect the hydrological model to what this is. When they say bird abundance, these are waterfowl. And same sort of thing is, as with water quantity and quality, there's no threshold below which wetland drainage doesn't change bird abundance. And what's interesting is that another thing that's interesting is that bird abundance decreases faster with the wetland drainage. And I believe that might have to do with the fact that because we're moving wetlands by area, that means if we move small ones first, which is what this scenario is, we're removing a higher number of wetlands than otherwise at the beginning and say we are. And you can sort of see that in the numbers and brackets at the bottom. So if you start with 46, then you move 16, then 10, and then 6. So that might have something to do with the idea of the signal that we detect here. So another thing that we're able to notice is that when, and I haven't shown this data, but we did do some wetland drainage scenarios over several of the basin classes. So pothole till, high elevation grasslands. We noticed that those slopes, that that sensitivity to drainage, the runoff and annual runoff sensitivity to drainage was different between the different land cover types. And so we were kind of wondering about that, and so it seemed to be related to landscape topography. And some of you in the audience may or may not know that much of the runoff that's generated on prairie hill slopes doesn't reach sort of major water courses or streams in an average year, and that's just because of the topography, the hummocky nature of it. A lot of times, snowmelt runoff will move down the hill slope, hit the first depression, and stop there. And what that creates are sort of non-contributing areas, and those are those areas in red in the inside of that map. What we found is that anything that's not red is what water managers on the prairies deem the sort of the effective drainage area. So you see that most of the prairies don't contribute in here. That effective area is fairly small. But what we're able to find is that the sensitivity of that area depends on landscape topography and wetland distribution. And as you sort of meet that storage deficit, that area that's contributing to stream flow in that average year, it increases. And the rate that it increases depends on the landscape. And you get this pattern across the landscape, that's shown here, where there's certain areas that will increase at a faster rate when that wetland storage deficit is overcome. And those tend to be in Saskatchewan, more on the sort of east central Saskatchewan, southeast corner. And that removal of this storage deficit, sort of imagine pastime. And it can be either met by filling the depression with water, like you do in wet conditions, or by removing its capacity. So what this map in essence shows is the sensitivity, perhaps, of different areas to drainage. So sort of coming back again to the point that maybe place matters. Right? There are certain areas where we need to be more cognizant of choices that we make that maybe others won't have as large an impact. And so earlier in the talk, I spoke about how mean annual runoff can decrease with warming, and just how important sort of future precipitation regimes are going to be for sort of the resilience of prairie communities to sort of that warming and perhaps drought stress. And what we're learning as we go down this road is just how important that the water that's held in wetland storage is actually really important for drought resilience. And if we look at sort of how we simulate, we took some simulated soil moisture content over that period that we simulated the hydrological model from 65 to 2006. And you can see in some drought years, sort of in the 80s or around 2000, cultivated areas, those are just consider those uplands, dried out quite substantially, and the only place that there really was substantial soil moisture on the landscape was in the depressions, and so they retain moisture longer than uplands during the onset of drought. And you can see in some places like the early 80s, when you get a long drought, eventually the whole landscape dries out. But the last things to kind of dry out are sort of those depressions. And this is really important because on the Canadian Prairie, much of the summer's precipitation comes from recycled water, basically thunderstorms. So convective heating of the ground evaporates water from what's in the soils or in depressions, lifts it up into the air, and you create thunderstorms. So maybe up to a third of it. A third of the rain comes from these local sources rather than being sort of brought in from the west, from the Pacific Ocean, or up from the south from the Gulf of Mexico. And there's a fellow named Rick Raditz from Manitoba some time ago found that this Bowen ratio, which is the ratio of energy that's used to heat the air versus evaporate water. So this is sunlight and heat coming from the atmosphere that warms the air, warms the air, which we all sort of sense as warmer temperatures, or it evaporates waters. And that relative rate is indicative of the chance of thunderstorms and that fraction of rain that can originate locally. So I'm hoping that this figure helps sort of illustrate some of this, is that if you have a wet landscape like 2012, which wasn't really a drought year, but it was a year where the landscape was quite wet, and you imagine having sort of a year of low precipitation, because that landscape is so wet, Bowen ratios tend to be quite low, and you get a lot of evaporation and enough, so the right sort of relationship between the surface and the air that it lifts that water up into the atmosphere, and you get this sort of positive feedback of rain that's coming out of the landscape. However, if you go into a drought and you don't have water storage on the landscape, that Bowen ratio switches and becomes quite high. And that red arrow sort of denotes more energy is going to heating the air than evaporating water, because there isn't as much water on the landscape anyway, and you don't get that recycling of water. So like I said, with the really hideous droughts, this isn't maybe going to help, but it might help get you through a dry spell or 1 year of drought better than you would otherwise by having sort of antecedent water available on the landscape. So if we think about this as in a resilience kind of framework, a landscape that has lots of wetlands, a landscape with lots of wetlands and lots of ability to store water, perhaps is, you know, if on the onset of drought, brought to the edge, but because there is enough water to support recycling of precipitation, what can happen is that you end up in that same sort of stable state and everything's relatively okay, and drought doesn't necessarily settle in. But if you're in a landscape that doesn't have as much capacity to store water on the landscape, that same instance takes you to that edge, but then it pushes you over, and maybe smaller stressors than normal are required to change that state. So sort of going from this two stable states that some people have called, that have assigned to the Canadian prairies, where it's either in a drought or it's in a deluge, right? And so whether you want to sort of end up in that sort of wetter state or the drought state, sometimes it does depend on how we manage this landscape. So I'm getting near the end here, and what we're hoping with prairie water is that we'd like to make some decision-making tools. So what we're hoping to do is place some of this in sort of an integrated modeling mapping tool, where we can put different scenarios of warming and wetting or drying, or say wetland removal from the landscape, and see how this might affect things like snow water equivalent or runoff. And we kind of envision this as sort of having a sliding bar, so people can see how things may change with different scenarios, and you can hopefully see how different parts of the prairies will respond, whether you live in central Alberta or southern Manitoba or east central Saskatchewan. So the implications of some of the choices we make, and not just sort of for next year, but also in the longer context, what happens 5-10 years out, and maybe we can layer some of these things as well. So it's, you know, what happens with climate change and wetland drainage moving forward, and you know, hopefully we can even work in not just some of the hydrology into here, but also things like nutrient loads, or again, the biodiversity, things like that, and hopefully, you know, as we discuss this with some of our partners and stakeholders, we can get this information into a form that's useful for them. So last slide, a bit of a summary, just a few take-home messages. Just that message that a diversity of wetlands is needed to continue to provide all those functions that provide the services that people value. And this is really important, is that place matters in terms of how watersheds respond to land use decisions and climate, and maybe ubiquitous policies aren't the best. Maybe we shouldn't design ubiquitous policies because they may not be the best way to use the information that we're generating. I shouldn't go too far down that road. They pay me to be a researcher, I should say that. And what's really important is that we need to think of this as sort of a combined agro-environmental system. If we swing the pendulum too far and say, okay, we're only going to care about the agroeconomy, then the ecosystem upon which that agroeconomy depends is going to be at risk. and likewise, if we switch the other one. And we need to think of it as a whole system and its resilience as a whole. And finally, this is kind of tangential, but I do want to put in a plug for LiDAR data. Many of the tools that we're finding that our partners and stakeholders are looking for require high resolution elevation data, which is spotty across the prairies. And we feel that a LiDAR elevation survey, which I think in Manitoba is starting to do quite a good job on, would be worth sort of the public investment for a number of reasons. And sometimes I think about the global positioning system as a nice analogy here. I mean, it was put up, those satellites were put up for a very different purpose than they are used for now, and society benefits from that public investment in many ways that we couldn't have seen. And I think having that data sort of publicly available would be quite a nice use of I don't know a nice public investment. And maybe I'll stop there before I get into too much trouble. So I'll shut down the talk for now. So thanks.
Thanks, Chris. That was a very informative presentation, and I see we have a few questions in the chat box as well as some hands up. So I'll maybe start with a hand up. Clint, you had a question. I'll unmute you.
Hi, Chris. Really good presentation. I think we need to find a good way to transmit this to the powers that be that actually make the decision with wetland and prairie water management. I live in the Assiniboine River Basin, and one of the things that you mentioned but maybe needs a little more clarification for people is the base flow, like the summertime flow in the Souris, Moose Mountain, Creek, Pipestone, Qu'Appelle, Assiniboine. That's virtually all from spring inflow being recharged from wetlands. And unfortunately, the easiest place to remove all our wetlands is near those river valleys and those places. So like this summer, we were down to zero flow in Pipestone Creek. And town of Mooseman relies on that. And I've been here is one of the main problems with draining wetlands, not flooding, but just the actual constant water supply. And it's a slow thing as far as how aquifers work. It's a slow process. You don't just see it one day when you lower those wetlands and the recharge, because it's a slow process. But how we get the policy to change, I'm not certain, but I think if more people understood the base flow issues and their water well recharge, they might go, wait a second. Anyways, thanks.
No, that's an excellent comment, right? And I'm hoping I was able to demonstrate, maybe not so much with the modeling. I think what we're hoping to do with what Misaki is hoping to do is couple this virtual basin model to a groundwater recharge model, so that we can run different scenarios and more explicitly show those relationships, and even if we can go so far as map that, how that manifests across the landscape. And link that up to some of the stuff that Grant Ferguson is doing with deeper aquifers, and the ones that would support the base flow and sort of the lower land. So people are working on it, right? And but I think we need to. I take your point that we need to be able to package this information in such a way that people can ingest it well and include it in part of their decision making.
Well, I was just going to mention, like, a very good analogy, what we're doing to our prairie pothole system here would be akin to saying we need to go and remove the glaciers on the eastern slopes and that forest cover and all that recharge mechanism for the North and South Saskatchewan, because that rascally water comes down there and floods people sometimes. You know, those wetlands, those are our glaciers of the prairies. That's what does the cycle. That's, like you said, that's what gives us the rainfall, and that's what makes where I live. This is parkland because the relative humidity is higher. It's not parkland because of, well, I mean, it's further from the drying effects of the Chinook winds, but we get the advantage of all that moisture evaporating off. But when we get rid of our permanent cover in our wetlands, that cycle has to be broken. It's just physics. Anyway.
Yeah. No, that's a good comment.
We have another question here. Would a confounding process be the moisture from evapotranspiration of growing crops?
Well, that's a great question about whether I'd have to think about that one, but that's a really good question because it all depends on when. Okay, and you're really stretching my expertise here, right? Because there's C3 crops and C4 crops, and when they kind of they go to seed, and when they're really drawing water and really transpiring, some and maybe people out there know better than I do. Well, actually, I'm sure people know better than I do. You know, some will do this in May, and some will do this May and June, some will do this in June and July, right? So some of it depends on this aspect of it, because, you know, if we also think about what the sun is doing, right, that prime heating period is the beginning of June, right? So maybe to answer your question, if those crops are heavily transpiring in June, then yes, I think you would get a bigger punch, so to speak, than if they were doing that later in the season.
Okay. Another question about the modeling. Does the model take into account less groundwater infiltration from compaction and salinity around the perimeter of certain wetland areas?
I remember we had a big debate about hydraulic conductivities with the change. I'm not sure that I think the way we set up the hydraulic conductivity model is that it was set by superficial geology and soil type, which we didn't change when we changed. So when in the model, what we did was if we removed a wetland, we assumed it became cropland, and altered certain things that way in terms of you know, the canopy, the vegetation canopy, but I'm not sure I don't think we changed the hydraulic conductivity too much for those kinds of things, but it is something that can be done. That's a good point.
Okay. Kyle, I see you have your hand up. If you have a question, just unmute yourself.
Yeah, thanks, Chris. This is a really important piece that helps make the case for wetland conservation, you know, especially as it relates to hydrologic cycle and groundwater recharge. And you gave a real good example there that I just want to kind of add to the St. Denis example, going from a class 5 wetland to kind of a class 2 wetland. And I think you went from going from duck habitat to being, you know, good for groundwater recharge. But I would just want to add that those class 2 wetlands are, well, historically, they're the ones we've lost the most of. And when it relates to biodiversity, this is why we see, like, you know, you also said that there was a steep drop off when we first start removing the wetlands. And I think that, you know, like just to speak to that mechanism, when we're losing those class 2 wetlands and smaller wetlands, which tend to be mostly class 2s and 3s, we're actually losing, like we're getting instantaneous landscape heterogeneity because we're taking the smallest basins that usually support a wider diversity in terms of shorebirds and passerines and shallow waders, as opposed to the deeper wetlands just supporting, you know, the waterfowl and some of the deeper water species. So anyways, this is super important information to convey to, you know, the decision makers, because we do need a wetland policy in Saskatchewan. And Lauren was speaking to that yesterday, and just tying in what you're talking about here in terms of hydrologic cycle to biodiversity should help us make a stronger case. So thank you for that. And I do have one question for you, and that is the Water Security Agency aware of this gatekeeper concept, and are they applying that when they're allowing drainage regulations to happen? And, you know, are they thinking about, okay, well, if we're going to allow half of them to be removed, let's make sure we keep the important ones? Do you know if they're aware of this and using it?
I think I'm gonna dodge your question as a federal employee and say I am so sorry, but I think we're you know, people like Etienne and Doug and Joe Mark, they, you know, we talk all the time. You know, and you know, I think we have a really good working relationship in terms of getting some of that information to them, and so I think I might leave it at that and say, you know, that's the, you know, speaking as an Environment Canada employee, that I know that those folks are working pretty hard on this. They have lots of things coming at them from all sides. So kudos to them, because it's a tough thing to manage.
I would agree with that.
Yep.
Okay, thanks, Kyle. Joanne, you had your hand up. Did you have a question? Just unmute yourself.
Good morning, Chris. Thanks for the presentation. I'm just, my question is regarding your model, and thank you for the other presenter informing us regarding the, you know, we don't have the wetlands policy, which kind of makes a lot of things very difficult for everybody, all the organizations and communities, because we don't have something to guide us. So, and that being said, this model you used, it sounds like a very good model. I don't know the variables behind that. However, with this model, are you going to connect with other different regions within Saskatchewan to model it? And second question is, what are you reaching out to anybody to do that ground data bit? Because I noticed you mentioned data, and data is a big thing that a lot of us are missing, and that's the important information that we need. And this model interprets so much, because I noticed you said the variables that you used were like the soil, climate, no tillage, and I forgot what the other ones, but yeah, because something like this, I think we all need in different parts of Saskatchewan, and data.
Yeah, I think because it's because of I think the role that or I guess our niche in the whole system, we didn't want to. We actually really struggled with this. There was lots of debates that went back and forth. You know, do we model specific places, or do we try to model how the region might respond and then use that? I don't think we're going to do that modeling, but what we can do is build a toolkit to help people who want to model do so. You know, right now we're working on building a publicly accessible data set for for people to do so, and even where we're going to put the outputs from our modeling for people to use if, you know, if they feel that that's useful to them. And we're in constant discussions with sort of the watershed stewardship groups in all three provinces about how to get this data in a form that's useful for people. Because I think if we do anything out of prairie water, if we can get a publicly accessible database that's actually used 10 years from now, I think I would be happy. And yeah, and the LiDAR thing, we debate that amongst ourselves whether that's our role or not to even advocate for this. But it'd be such a valuable thing to have that publicly available. Would be fantastic. I look to the United States, and I have lots of friends that work down there in the same field as I do, and the United States does a bang-up job with some of the publicly available data that Canada as a whole kind of doesn't, kind of nails it in, frankly. But if that's something that we could do, then again, I think that would, and it wouldn't just benefit like people in our realm, but I think it would benefit producers, it would benefit all sorts of industry to have that kind of data available to people. And from a more egalitarian point of view, yeah, I mean, people are collecting LiDAR data, but then it becomes like privately held. And I think that maybe, and I worry that creates inequities amongst different, you know, stakeholders on the land. And I think just philosophically, we should maybe try to avoid that. Anyway, again, maybe I'm drifting too much into policy, but I hope that answers the question.
Thank you.
Thanks, Joanne. Another question here. Does the Aquanti model that's been developed for the Assiniboine have a modeling system that would complement your research?
Sorry, you're kind of breaking up in there. I got that somebody set up the Aquanti model in the
Yeah, so
Assiniboine.
they're wondering if the Aquanti modeling system would complement your modeling. So I'm not sure if they're wondering if you use the Aquanti model or if it's similar to what you've used or you could use it.
Yeah, no, I think it'd be, you know, and there's actually several groups that have, you know, attempted to model the Assiniboine. And I'd be super keen to sit down with people to see what kind of results that they get and compare them with ours, right? Because I think if what we can do is, you know, I don't think our our approach has not been to run an ensemble of models, but like I said, there are, and as you know, as mentioned, there are other people modeling these systems, but maybe together we have an ensemble that maybe we could share, or at least compare notes, and if everybody is kind of showing the same thing, it reduces that uncertainty and it sort of increases the volume in the room about, you know, some of the, you know, these are the implications of climate change or land use decisions that we make, policies that we have, that kind of thing. So I think that would be a valuable exercise for sure.
And one last question, and does it rely on having LiDAR data for best results, you know?
No, I mean, we can live without LiDAR, but I think to best answer some of the very local questions almost requires LiDAR. There's some really good digital elevation models out there right now, but even those have trouble picking up some of the nuances on what is a relatively flat landscape. You know, I'm always loath to say the prairies are flat because they're not, but they are relatively flat, and there are places where having that LiDAR data is super important. It just sort of would take things up a notch in terms of confidence in model outcomes.
Great. Well, thank you so much, Chris. That was very informative. We had some good questions. I think we've come to the end of the webinar today, so I want to thank you very much for your presentation. On behalf of the organizer, the Citizens Environmental Alliance, and the supporters, as well as myself and Ducks Unlimited Canada, thank you once again.